Okay, I think it's time to start the session. Welcome everyone. Um, First of all, we do have some shared PPT slides and also workflows in Colab. So the second half of the session will be a kind of interactive session. You can do some hands-on. You can try the notebook we created, and you can even make some adaptations. You can try new parameters to get your own result. So if you want to have access to the code and also the shared PPT slides, you can first check into the agenda, find the session at here, and then you can go to the collaborative notes document. It's hide somewhere in this tiny button. Click it, and you can find the shared Google Doc at here. And then we do have those links pasted in this shared Google Doc where you can find everything we're going to talk about and also the resources. So before I start, may I also ask you to just check in. Please put your name and your abbreviation on the top of the document. Okay. Okay. So hope everyone can find this document. Go to the agenda, click the link of the session in the agenda, and then in our session document, you can find a collaborative notes document, the link is here. And once you click it here, you can find this Google Doc. And where you can find all the links to the resources. Good. And also, I just want to check anyone online. Can you hear me clearly? Okay, otherwise I will just go ahead. So let me begin my PPT slides. Oops. How can I share? Okay. Things sharing. Good. Okay, welcome everyone. So our sessions, the big topic is about using large language models together with the open data surface of a database called Mindat. My PhD students, Jin, and myself, Marshall, we will give the talks and then organize the interactive activities of this session. But first, let me give a quick overview about the database and also the open data surface we have built in recent couple of years. The database is called Mindat, mindat.org. Some of you may have heard about it before. And then the Open Mindat project is funded by NSF through the S-Cube program. Wait, I guess I need to come here first. Yeah, Mindat was created by Julian Roth about 25 years ago. This is his lifetime project. Sometimes I even feel jealous about him. He made his personal interest into his career, lifetime career. But now Mindat is really popular database. I think it's one of the largest database about mineral species and also the distribution of mineral species on Earth. Here you can see the quick statistics we made in 2023. Altogether, it has about 27 TB datasets. Why I need this? Oh, so those include mineral species, their distribution, localities, and also a lot of images and photos. And in recent couple of years, the technical team also tried to incorporate records about rocks, geochemistry, paleobiology, and also a lot of map surfaces across the world into the database. So you can see there are a lot of web pages about those different topics, more than 19 million web pages. And the usage is really high. You can see last year, the whole website has about 65 million page views from around 10 million unique users. And then another big part of the database is crowdsourcing. There are about 27,000 registered users, and about 7,000 of them, they are active data contributors. And data quality is a really big issue. And Mindat has about 60 experts. Many of them, they are research scientists in museums across the world. And some of them, they are retired professors from universities, mineralogy or geology. And they spend a lot of time taking care about the submitted records and make sure the data quality is good before they are released to the public. And for the Mindat project, Open Mindat project, we have do several works to realize the so-called semantic harmonization. In the past 3 years, we have looked through the general subjects and also the data qualities of all those subjects, and we try to employ community level standards, vocabularies into this. And for the front end, we also leverage schema.org and OGP Open Graph Protocol. This one is by Facebook. Schema.org is from Google, Yahoo, and Bing. And we also deployed persistent identifiers to the website. And we have also collaborated with some stakeholders, including both other open data portals and research scientists in the field of geology and mineralogy, and we made some breakthroughs in scientific research. Here is a very simplified diagram showing you the key data subjects in Mindat. So you can see mineral species, epsilon is the number one, and then locality, and then mineral occurrence. So if you find a mineral species at a certain locality, that's a mineral occurrence. And then besides this, there are also fossil records, rock records, and a lot of images. And from outside as computer scientists, we think many of them, they are relevant to spatial science and also temporal science, so space and time. And here is a example to show how OGP was deployed, the Open Graph Protocol released by Facebook. On this web page is a mineral species called orphanite. I just show the source code. You can see how I believe some of you are doing the work about the front-end website. I think you might be familiar with. This is just HTML, but we write code to do this automatically to all the mineral species and also mineral occurrence records. And the big advantage of this is when people share a link, like here I just paste a link. I did just tried it. I paste a link to my Facebook timeline, and you can immediately see like a thumbnail of this web page, as you can see here. And also those kind of machine readable metadata annotation also is a good advantage for search engines. For example, Google, if you search this mineral species name, in addition to Wikipedia, I think sometimes Wikipedia is always on the top. And then, but for mineral species, normally you can find a link to Mindat on the first page of the search results. I think one reason is that we have those machine readable metadata annotation on the web pages. And we have also deployed identifier surface. And actually, you can see the identifier here, like for cores, the Mindat identifier is like this. And it's very interesting, even before those kind of identifier were deployed, Mindat because it's a relational database, and Julian Roth and his colleagues, they have already deployed a kind of unique naming rules to the URL. So they have code for different data subjects, and they also have a unique identifier for each record. So here, for example, mean that, and then colon 1, colon 1, colon 337, colon 0. Each code has a kind of meaning, as you can see in this table. The first one, mean that is the namespace, and then the second one is here, is 1. It's the authority of the identifier, like here is from MinDat. And then the second one you see here, it means the data type, and here is mineral or geomaterial. And then this 4-digit part is the unique identifier or the unique number for this mineral species. And last one is just a checksum. Sometimes they may be derived names or abandoned names. We just use this as an additional digit. And how does this work? As you can see, it's just similar to the fundamental semantic web. For the namespace, we can just replace it with root URL, and this made it resolvable already. And also we have deployed UUID to mean that, and they're also resolvable. And then those kind of unique ID, even just the 337 for mineral species, we can also use it as an identifier to do queries to the Open Data API. That's another big part of our Open Data Service work. You can use this as an entrance to query the API. Okay, so next, let me just quickly go through the work we have done with the API and then the R and the Python package. Because originally the database is very popular, and you can see there are a lot of users to the front end, but the back end is never fully open. Just in the past decade, Julian received a lot of requests from the Geoscience community saying, can you share a part of your database to us? We want to do research on this certain type of mineral species. And this made it really hard for him because he has only one backend, and the front end website is built on top of the database, and he cannot make it fully open. So through this NSF project, we have set up a structure to do the open data service. The fundamental work is API, and now is fully running. And after that, in our team, we also built Python and R packages for queries to the API. And initial versions of those packages, they are already released on CRAN and also PyPy. We have both Python and R packages. And here is a function in the R package, is to retrieve a list of all those mineral species ratified by the International Mineralogical Association. Now it's very quick, just in 10 seconds, you can get a list of more than 6,000 records, and each of them has about 15 variables. And we can do more use cases. Basically, just like functions built on top of the parameters in the API. But we make this more friendly to end users, especially those working on mineralogy and geology. And we have also collaborated with some other open data portals like RAF, GeoRock, and EarthCam, because sometimes on their data portal, they need those kind of standardized lists, like the mineral name list or the hierarchy of rock types. And now from the MinData API and also the R and Python package, we can easily output those kind of vocabularies, or sometimes we call them knowledge graphs, for the other open data portals to use. And next, I want to show you some interesting applications of machine learning on the MinData front-end website. is a case study called mineral association analysis. Some of you may have heard about association analysis. This is very popular on social media and even online stores like on Amazon. You may often see those kind of recommendations say, oh, people who bought A, B, and C, they also bought D. So, like similarly, here Sean Morrison and Anil Prabhu, they study the mineral core occurrence patterns among a large number of localities. So they can find the rules about the core occurrence of mineral species. And now, if you are giving a new locality, and you can see, oh, there are already a number of mineral species occur in this locality, and then what is the possibility for some other mineral species to appear in this place? So what is the possibility for me to find what type of new mineral species is here? They build a model, and they get some really good results. They get a paper published, and then Julian Raff and the Minder team, they say, oh, this is a really good study. And they simplify the process, and now they deploy this algorithm to a really high level. So for more than 40,000 localities, we can see this kind of prediction results. Later, I will show you a use case. And then the second one is called paragenetic modes of mineral species. Bob Hazen he's an expert in the field of mineralogy, and he summarized a list of 57 paragenetic modes among almost all the mineral species. They show the diversity and the distribution of mineral species, and also their evolving formational environments. And Julian Raff also simplified the procedure and deploy this to all the 400,000 localities. Okay. Next, let me show you an example. I just made this morning. Seems not very far away from here, just the northeast of Asheville. There's a really large mineralization zone. And I mean that I can find a locality called Sprouts Pine Mining District. And there's a web page for it. So you can see here exactly. And if you are browsing the slides, actually, you can click this link or paste the link and see it in your web browser. So for this mineralization zone, there are now 99 valid minerals. And then in the predictive mineralogy, we can see what is the possibility for us to find some new mineral species at this locality. And the result is based on the association analysis. It's kind of a machine learning result to do the prediction. And this table shows you the prediction of the potential paragenetic modes of deposits at this locality. This is just like a reverse of Bob Hazen's work of the 57 paragenetic modes. And how did we get this score? Is basically for each paragenetic mode, there's a list of mineral species. So for this certain locality, if a mineral species appears, we assign a score to the result. So you can see if there are more mineral species in that paragenetic mode appear in this location, the score will be high. So that's why we can give a list of those results. So for sure, if a certain mode has higher score, it means there's a very high potential. For this locality, we have this paragenetic modes of mineral species or paragenetic modes of deposits. This other type of thing. And just in the recent 2 months, the Minder technical team also built another interesting visualization, the network visualization. And here is the source data is also very interesting because on MinDat, there are a lot of photos or images of specimens, and many of them they are already tagged or labeled by experts. And here you can see it's also for the same location. I think for this location, there are already around 900 photos of specimens. And then here is if for a certain specimen, if there are 2 or more mineral species identified in this photo, and then in this network, there will be a link. This is the network here shows the co-occurrence of mineral species among the specimen. And actually it's the photos of the specimens. And there's even a slider at here. So for example, because some mineral species, they are just so popular, like I think for many localities, quartz is always the number one mineral species. They are just everywhere. So if you don't want to see the quartz in the network, you can just move the slider here. Like here, I just move it to the left a little bit, and this will remove quartz from the network. And then you can also zoom in or zoom out to the network. It's interactive. So that's some work we have been doing in the recent 3 years. As I mentioned, MinDat is such a big database, but still, when we look back at the records, we can still see sometimes we even call it a bias of the records. As you can see here in this map, the topic here is the density of MinDat localities. You can see US, Europe, and Australia. Those 3 areas have the best density of locality records. And there are some reasons. I think one reason is because those areas, they have the best records written in English. And also there are more like enthusiasts or users in those areas. They like to contribute records to the database. And for some other areas, like especially the big south, like Asia, Africa, and South America, there are some records, but absolutely they can be more records contributed to MinDat. But there's some reason because language is one issue, and also user activity is another issue. So if we have abundant records for all the areas across the whole world, we believe we can do more interesting data mining or machine learning studies. So that's a quick overview about the MinDat work we have been doing. Last, I just want to show you the so-called cyber infrastructure ecosystem. This is a diagram conceptualized by NSF. So CI is not only about data or the facilities, it's also about service or the friendliness of the service, and also people, including both the data contributors, service providers, and users. I think that's also why between me and Jean, we saw the potential of using large language models to improve the friendliness of the open data surface. And in the recent 3 months, we have made some progress deploying large language models in the open MinDat data surface. So next, let me ask Jean to give the presentation about, because that's the topic of this session.
Okay. So thanks to Marsha's comprehensive introduction to MinDat. Now I'm going to share my, let me see. Where is it? Oh, no more. No, I found it. Got it. I mean, where is the Zoom now?
You play it
Yes,
first.
I haven't started sharing. Just share the screen one. What's that?
Okay.
Okay, sorry for waiting. So thanks to Masha's comprehensive introduction to Open Minda service, now we can jump to our main theme of today's session, which is just utilize the large language model in the workflow of so-called Earth data analysis, but we're taking the Open Minda API as a use case. So as a quick background introduction, I'd like to say that because of the launch of the ChatGPT, many interests have been attracted to this domain. And in addition to just to chat it in a dialogue, many applications has been made, especially in, say, using the large language model as a co-pilot when you are programming and doing the data analysis. But we just want to incorporate such kind of workflow more deeply in the Earth data analysis. So therefore, we can trying to conquer some limitations of the common utilization of large language model in the data analysis, such as the data cutoff and limited control and many more. So in the proposed workflow, we are trying to tackle these challenges. Say we want to reduce the time for the users to instruct the large language model how to answer their questions in a more, say, meaningful sense by using the RAG technology. And in addition, we want to address the uh, difficulties for the users who are with limited programming skills when using our powerful Min.dot API. That is to say, they can make the complex data query using just simple human natural languages. And in addition, we want to push this application one step more, not limited to just do the data query. We want to display some preliminary data analysis result in this workflow. And let me start with the knowledge retriever part. So let me quickly go through the essential idea for this approach. The RAG, the retrieval augmented generation, is somehow well in between the traditional large language model and users dialogue. We are trying to retrieve the context relevant knowledge from an external knowledge base to the dialogue. That is to say, the ChatGPT, they don't have to answer the question based on what it has been trained, which is somehow roughly the entire internet knowledge. We can link very precise and very specified knowledge and to this dialogue. Therefore, they can answer this question more relevantly. Here's a quick use case. I can see I randomly picked this paper from the journal Nature Geosciences, and I created two questions. As you can see, you don't have to read these questions very, very in depth, but these questions are essentially not able to be answered perfectly by the GPT without the relevant knowledge. And here is what the coding screenshot for our workflow. You can see the GPT-4, after applying the RAG technology, can answer to our question with a very relevant and scientifically meaningful responses. And if you dig into the details, you can see that the relevant paragraphs from from this paper has been already retrieved and put into the context of the ChatGPT. Therefore, they can read. Actually, they can read as a human, read the paper and answer the questions accordingly. And this is just a brief introduction to a preliminary usage of RAG technology. And now we are going to do a somehow more meaningful comparison, not only using the leading online large language model service, we also do the similar experiment on the open model. We are running the large language model locally, which means you can run them on your laptop or some other more convenient personal device. And the reason we are trying to do this is that, we can see the online large language model service are used to have a much more better performance compared with the open model, because they do have a much larger size and much more parameters. And but if we can match the performance of the online service by running our local model, we can gain such kind of advantages. Say we can have our data private and in secure situation. And one of the most important part is the cost efficiency. So just I'd like to mention that for today's interactive session, I just charged $30 to my ChatGPT-4 account. But if you can make this entire workflow run on a local environment, there will be zero cost except for your electricity fee. So in this quick experiment, we just list these three very common open models: Mistral, Gamma, and Llama, which have relatively less parameters compared with the GPT. But you can see the result is amazing. The experiment setting is that we are just comparing the generated responses of GPT-4 and three other open models. And finally, we will ask another brand new GPT, which has no knowledge about our experiment, and you can read the answers from these models and evaluate them with some reasons. You can see here is a screenshot showing how our open model, this time is Mistral, answering the question with, you can see here we incorporate the knowledge base, which is just the paper I mentioned before, as it is knowledge base. Therefore, you can see Mistral can answer the question in a pretty neat way. And here is a grading result. You can see the generated answers grading by GPT-4. The first 2 points is why the generated answer is meaningful and well, sound and perfect. And the second 2 points by GPT-4 is criticism. So about the generated responses, and the overall grade for this generated answer graded by GPT-4 is 8 out of 10. And here is the all the evaluating result of this experiment. And as you can see, not the GPT-4 will achieve the best, only will achieve the best result. Mistral and some other models can also match the performance of the leading model when a very relevant context is given, which is in the background of the RAG technology. That is to say that in such kind of specific application circumstance, that we can somehow rely on the performance of open model. And so then jump from the knowledge rack, we are trying to help our large language model workflow can connect to some online services, say the data API. And here you can see that we are trying to tackle the complex data retrieval process using API. So here, the GeoLex is a very good database for recording many lexicon of the earth science field, especially for the formation knowledge. And they do have many geoformation knowledge for different continents and in different languages. But applying such kind of data querying process using program can be a little bit complex for many people, because they will have to read the API document and run the code. And in our compiled workflow, you can see we can merely input such kind of question, and we'll have a relevant responses generated by the GPT-4. And here's what happened in the background. You can see when the user essentially input their request to the GPT, it will ask a action node called the geolex search, and it will automatically assign and automatically create the API call to this tool. And finally, after retrieve the relevant context, the GPT will read the result of the API call and answer the request question to the user. And just just showing this part is the old code we need to apply such kind of large language model function coding. That is to say, such kind of workflow can be easy to scale up to many other kind of API coding, which is showing the scalability of our workflow. And in addition, we also make a comparison experiment. Say the human asked the GPT to answer a very specific question about formation nutrient, but without coding a function. Well, when the user explicitly asks the GPT not to code the function, it will just answer that, I'm sorry, but I can provide such kind of knowledge because without the function coding. And here you can see in the past years, we have spent many times developing the OpenMinter API. Is trying to make this entire data query more user-friendly, but we have already promoted this in AGU, EarthCube, and many other conferences. And one of the critical feedback from our users is that they are still complaining that such kind of API is hard for them to get their hands on. So here's the result. We managed to apply the large language model to this process. Therefore, the users can do the similar query using the human natural language, and the large language model can do the response accordingly. And here's what happened in the background. Similar to the previous use case, the large language model will code the correct tool and generate the answers accordingly. And finally, this is what I mentioned, that we want to go one step further, not just limited to the data query. We finally create such kind of a network shape-like workflow. You can see we applied a AI agent called supervisor in the middle of the network, and whenever user input their request, the supervisor will read the request, and it will decide which tool can be used to execute the user request. And say each of the roles are optional. That is to say that this workflow is relatively very flexible. Here is the quick use case demonstration. You can see whenever user want to plot the histogram of the mineral elements, here is the following result. But you can see that this result is achieved by such kind of complex process. The supervisor will firstly decide it. Now the user want me to generate the histogram, but I don't have the dataset in hand. So firstly, you will call the collector to collect the dataset, and then the collector will respond to the supervisor, say, "Hey, I've conduct this data query, and here is the result." So the supervisor will then think, rethinking that the user wants the histogram and now I have dataset in hand. Then what should I do next? And here you can see that the supervisor automatically select the plotter to run the visualization process for the user. And finally, it will come with the result of the visualization node and end up with the histogram. And in addition to the histogram, we also make our workflow very flexible to the user request. You can see here is a relatively very complex never mind. It's a relatively complex data query from the user, and the demanded task is different to the histogram. We can plot the network. This is interactive. You can see this in the following interaction session. And here, in addition to simply plot the mineral information, we also make our workflow is compatible for plotting the mineral locality records, and we can plot the heat map for the record. And I don't want to go too deep for this because this visualizations is what you are going to put your hands on and you can play with it. So if you haven't logged into the to the interactive document, please go scan this QR code. And if you are already in that interactive node, please direct yourself to the resource section. We do provide the Colab demonstration link there. You can just use that Colab notebook and play with it. We have a very detailed quick stop guide incorporated to that notebook. And I want everyone to try, say, such kind of query or input to the large language model and see what our OpenMin that workflow can end up with. And just, I say, user feedback collecting. I'd like to hear from you that what kind of input will end up with somehow illegal results. Therefore, we can revise our workflow accordingly. Thank you.
Thanks, Jean. I think next we still have about 45 minutes. I think that's a good time to let many of you or even each of you to take a try of the Google Colab notebook Jean shared. So if you want to access, I think it's somewhere. If you're in the Google Doc, you can just come here, click this one. Is this the correct?
Yes, so here is where you should find our.
Isn't that the same?
No, yes, go for it. This one. Let me do it. Okay.
So many of you are still running the demo. Just some additional comments. So you can see our work is just a very unique use case in the open data service or in the open data ecosystem. Mindat is very unique because it's crowdsourcing and it already has a really big both contributor and user communities. So the database actually is a really good example of open data service. But still, you can see when we try to use large language models in the data service, for sure, we still face a lot of issues. I think they are relevant to the theme of the ESEF meeting of this year. It's like ethics, like for some records on the open on the Mindat database, we are not allowed to make them fully public. For example, the pictures or the photos of mineral specimens. On the front end website, they are actually open. You can browse all the images, but most of them they are still copyrighted. Some of them is free to use. You're free to download, but most of them they are still copyrighted. So the original contributor they have the copyright. You can browse. We make them open, but mean that is not allowed to make all the pictures open for download in a batch. So we still have those kind of ethical issues, and that's why from the API you don't have access to the images of specimens. And another one I think is the trustworthiness, or it's kind of friendly, like right? So using large language models is a good way to increase the friendliness of the open data service. For end users, you can just, once everything is set up in a good way, you just need to type questions in natural language. This makes it really easy to realize some very complex tasks. But then we face the issue of trustworthiness. How should I trust the result generated by AI, generated by large language models? So I think that also open a lot of questions for us to explore. Gene, I think, already tried to make some progress in that. Like we can make the whole workflow open, like what are the training data set we use and how we set up the context for the large language models, what are the input data sets from the API and where did we access. Like in his workflow, actually you can see before you run the QA session at the second half, in the first half, you can see how in the workflow we set up the context for the large language models. So where is the data source and how they are downloaded or accessed from the Mindat API. But still, there are many questions to be further explored. So if you have any feedback or follow-up questions, we still have some time. We can discuss now, or you can just paste them in the Slido platform for this session. Yeah, Kate?
Say something about reproducibility of large language model results.
Yeah, you can do it.
So the reproducibility is somehow relevant to the so-called a parameter called temperature in the large language model workflow, which means the temperature, if you say this as higher, the large language model can be more creative, but somehow they will generate more random answers. That is to say, even if you input the same request, but in different time, you will get the different results. So one of the solution to this is just somehow relatively reduce the temperature. But if you reduce to zero, it will somehow cause some problem, because you can see in the workflow, we can apply a strategy called the large language model revision, which can make them to revise themselves from the error they encountered, and it can automatically revise the user request or automatically revise the workflow to ensure the user request is executed correctly as a result. But if you set the temperature at zero, you cannot make any self correction anymore. So, well, tuning the proper temperature for the large language model is a good question, and we haven't studied this very deep yet. But because they can, currently we're just using the default temperature. I believe it will be 1. So and we can find the result can be relatively consistent and acceptable. So I think this is not a big deal. But in the following plan, we do have a plan to move this entire workflow from the GPT to an open model workflow. In that case, the model, because they are not as good performance, they do not have the good performance as the GPT-4, so they will demand more strict fine-tuning, including the temperature tuning, and which will be in our next step of the research. Should I go or ask me or?
Sure. Either one. I think you brought it up first, but this was about we're discussing how the language LLM is like pulling from a knowledge base.
Yes.
In between that process of aggregation LLM. So when we're in this Colab notebook, when we're making a request, is it accessing for each request the knowledge base for that specific request, or is it just going on whatever?
Well, I have to say that the rack part isn't included in the notebook I provided. It was in another notebook. So, well, you cannot test the rack part in the notebook today. But well, I have to say that the rack is the reason I didn't include it in the notebook is I think the rack part is relatively preliminary, because accessing the external knowledge base in the large language model workflow is a very simple part. So each time, the essential idea behind the RAG is actually whenever user create a request, the large language model can firstly they will read the user request and compare the keyword or the key concept of the user request to the knowledge base and find the most relevant part, say somehow like a vector cosine similarity comparison or just a similarity comparison, and retrieve the most relevant paragraph along with the user request. The large language model can read the user request and the relevant context, and then it will generate the so-called augmented responses to the user. That's the process.
What I'm seeing when I submit a request, it will put something like in a JSON or something, and it will, I think I see parameters, like it's transforming my input into a set of parameters, like what the history or element distributed of IMA. When I'm running it, I see this JSON string, and it says what the hardness is. The hardness maps it. So is it constructing that before it reached the LLM, or the LLM constructing that from my string? At which point?
Thank you. That's a good point. The JSON part is generated by the LLM. So we just teach them that here is a structure, the structure we can use to code the tool. So the large language model can read the user request and read the structure and manually just extract the parameters from the user request and feed it into the structure. So this part is entirely the large language model powered. And the reason we are using the JSON to query is that we are building this workflow on the OpenMinDat API, which takes the JSON as a query parameter.
Gotcha, that makes perfect sense. And then my last thing would be just where would that knowledge base concept fit into this? Would it be verifying these parameters, or like how would the knowledge base be as like a context system for the LLM? Or does that make sense?
For the RAG, well, we cannot manipulate many details in the process of RAG because essentially the external knowledge base, say a manuscript, is automatically embedded to as a vector. This part is automatically setted. The only thing we can do is we can change to different embedding model. Therefore, we can result in different embedding spaces. Therefore, it will end up with different similarity comparison results. So, as I mentioned before, the RAG is somehow before generate the responses to the user, it will read the user request and compare the user request with the embedded spaces and find the most similar part to that question and retrieve that part plus the user request and generate the responses accordingly. So yes, so if you are looking for a different embedding space, just switch to different embedding model. That's it. That's everything we can do.
Still have one more question.
So I know you talked about training that very curious that show us.
Oh, so you are asking about training? Well, in the context of large language model, it's more commonly addressed by the term fine tuning. Well, this part is entirely the prompt engineering, which somehow we just manually put everything we think the large language model need to know about the API document and how to deal with the user request. And we didn't apply any fine tuning. This will result in a good advantage. Say we can easily switch this entire workflow to a different model. Say in addition to ChatGPT-4, we can try compare the performance to GPT-4, GPT 3.5, and other model like Cal 3, Cal 3.5, and many more. And yes, fine tuning is also in our plan. And especially we are trying to apply the fine tuning on the open model, which means, well, we already built the entire workflow on the open model. The reason I didn't brought it to today's session is that it would requires you to download around 4 to 5 gigabyte size of the model, which can be time consuming. So today, just for convenience, I just only show the online model version. But in our open model, we can do the similar workflow. Say you can ask them to plot the histogram, heat map, or whatever. It's relatively same. But the only difference is that because of the performance limited, the model size limitation, somehow the open model can go crazy. So with the same request, somehow they will end up with a dead loop or just cannot parse the user request correctly. And somehow we do told them to code the tool using the JSON, but they will insist to code the tool use JSON but with totally different struct. The reason I found, I guess, to this circumstance is that the open model was originally trained on some other training data, which is somehow polluted our prompt engineering. So I think the fine tuning for the open model is inevitable and very necessary to help improve the consistency and efficiency to our workflow. And yes, I do have one idea about this. This idea is actually can I say that? It's my founding Friday? Well, well, I'm trying to propose this idea later. And well, according to this session, I also have my poster about this topic in the afternoon of the Wednesday. So anyone has any problem or any interest can come to poster session and discuss with me. Thank you.
Okay, maybe the last round of call. Any comments, questions? Otherwise, oh, yeah. Go ahead.
So how do data set metadata traffic training or foundation?
Well, you're asking about the metadata?
Yeah. So how might different either presence or absence of metadata sets impact their use or trust?
Well, well, because this workflow is especially built upon the open min.data API, which that is to say we do not have to dealing with miscellaneous different data structure type. So there is not many to do with metadata parsing. So because we are just using one unique data portal as our data source. So if we plan to add support to some other more data API, say the rough or one geology geochem, we do need to somehow pay more attention to that. But currently, we don't have to bother with it. Thank you.
Yeah, I can make some additional comment on that one. So that's because min.data is already well organized, because in the project, the first stage of the open min.data project is like a very thorough review and cleansing of the records, including the metadata records. That's why when we set up the API, all those data structures, parameters for data queries, including those community level standards like the IMA approved mineral name list, and also the entries of like elements, formulas, hardness, all those kind of parameters related to mineral species, they're already a part of the API and also the entrance for data query. I think that's a really good advantage for Gene to build the large language model applications, because the metadata is already a part of the API. Yeah. But also, as he mentioned, if we want to scale up to other open data resources, we may need more time to look through the situation of them. Like, do they have a really good API service, or is like just like a traditional relational database, or even like a chaotic situation, like a literature resources? We need to have different solutions. Yeah. Okay. Yeah, I think I can do some quick wrap up. The first is open min.data resources. Now they are available. So if you are a researcher in geology or mineralogy, you can take a look about the API and also the address for the R package and the Python package. You can find them in my PPT slides. They are all open online now, and also you can quickly just import them from the R environment or the Python environment, just one line of code. You can load the package and you can run the functions from the packages. And then you can build up any kind of applications you want. And second is from Gene's presentation and also the demo, I believe we can see the positive utility of large language model in open data service. Absolutely, we can see the direction of using large language model to build friendly open data service for domain specific fields like in mineralogy or geology. We can even think about the potential in other domains, biology, or any domains has those kind of open data services. But still, there are many other topics or potentials to explore. I think that's why for this year, ESAP set up the theme as trustworthiness and reproducibility. So I think for large language model application, we also face the same topics: ethics, trustworthiness, reproducibility, and others. So finally, if you still have any, so even after the end of the session, please still, if you're interested, please still spend some time trying the demo. You can change different queries, or if you are getting more familiar with the API, you can even dive into the details of Gene's codes, make changes, and then build your own workflow. And if you have any other questions or feedback or comments, you're more than welcome to contact Gene or me to send your comments. Yeah, that will be a really big help for Gene. Yep. Thank you.